So this is the lesson for transfer learning and pre-trained models. Today we have a new repo. If you have this link, you can go here, click on code, and then open with GitHub Desktop. The repo for today is really, really huge. It's probably 600 MB. So when you're ready, just click clone. This will take a very long time. So I already have mine on my computer. Just gonna let this download. So it will look like this. You'll have a folder called datasets, a folder called images, models, and weights. I have done some of this stuff for you just so we can practice together. There is two datasets. We have one called fruit dataset and one called vegetable dataset. There are details of where I got this vegetable dataset. This is from Kaggle. If you go to this link, you will see the original page. It will explain what it's about. This is a vegetable data set with 21,000 images from 15 classes, and they have already done a test, train, and validation split. I've just gone with what they have split. They had the 70% with 15% 15% ratio. So just gone with exactly this ratio. I haven't done a new split. So if you want to do a new split, you'll have to put these folders back into one folder and then use our split notebook to resplit with your own ratios. So I have a fruit data set, which is the one we have originally. This time, the images are 224 by 224, they're a little bit bigger. Apart from that, we also have some scripts here. So I'm going to go through some of this stuff so that you can understand what it is, and then we can sort of go through the script together. So transfer learning is a process of using weights from a different data set so that you can train with your own data set. When you use transfer learning, what you're trying to do is you have a model that was trained from one data set with a different sort of weights, and then you want to use those weights so that it sort of enhances the accuracy of your own model. And we do this because sometimes we don't have enough data in our own data set. So with transfer learning, there is a script here. What we're trying to do is we're trying to use the weights, which will be from the vegetable ones, and we're going to use them for the fruit ones. So if you go to TensorFlow and you go to Learn, Introduction, and then Learn More, underneath Vision, there are tabs for transfer learning and fine-tuning, as well as transfer learning with TF Hub. And they offer some kind of like guideline on how to do this. They have their own guideline. What they're trying to do is they're trying to use a model that was trained on different types of images or common objects, and they're trying to predict cats and dogs. And TensorFlow has a hub of its own where you can get different types of models, for example, MobileNet or Inception, and you can use them with their own specific weights to be able to predict different types of, I'd say, classifications. So apart from this specific TensorFlow hub, when you go to search and you search for applications, you will see a list of those same models and you'll be able to pick from these different ones. I'm just going to select the first one, which says VGG19. And on your left side, if you scroll down a little bit underneath applications, you'll see a list of different types of models. So for today, we're going to specifically stick with MobileNet V2 because it is small and it does not weigh a lot. So when you download it, it will take less time. However, if you have time, download VGG16 as well. It's the same process. We'll go through it together, but it just takes a little bit more time to download. So we're going to stick for now with MobileNet V2. So the first thing would be to sort of understand what are these weights. So inside of images, we have some descriptions. We have talked about inputs and outputs. When it comes to input, input is the data you feed the model. For example, your images. Currently, we're using images to feed our model. The model itself is the network of the interconnected neurons. So all of those little circles with lines, all of them represent this one big model. And the output is what we want, what the result, the prediction. But the weight are the numerical values associated with each connection between the neurons. And when we look at them in the second image, two dot weights, we can see that every line that goes from a neuron to a neuron is a weight. And it's like a number that describes how heavy that line is. And that neuron will fire from that, let's say, synapse to the other neuron based on how heavy that line is. And when it fires, it creates a chain, and that chain gives you a certain output direction. So if the input, for example, this is your one image, and that one image was a cat, for example, it will maybe hit these different lines all the way to here. Let's say this was the cat output, and if it was a dog, maybe it would hit these different lines so that it would be a dog output. So the weights describe how heavy those lines are so that you can create that pattern to be able to go to that output. And technically, if you don't have enough images, you may not be able to create the right weights. So what we're trying to do is we're trying to artificially create those weights using a different data set. And then after we have, let's say, gotten enough accuracy, we can then override those weights by keeping our own images. So then they can sort of feed over those weights. So what we're trying to do is we're trying to override those weights with our own weights, but we're not trying to do it from scratch. We're trying to do it bit by bit. So the first step is to actually get those weights. So in weight training, there is a script. I might go through this. I might not play everything so that it takes less time in the video. But when you're going through it, please play everything. So first step would be to have some of these libraries. If they're already installed, it will not take any time. If you have not installed them, this will install them for you. Then what we're trying to do is we're trying to use the vegetable data set to create these weights. So I'm going to play this. What you're trying to do here is you're trying to set these settings. This is one setting that becomes, I'd say, stuck with you with your new model. So if you say that I am going to create weights with an image size of 32, that means you can only use a model with this size. So with 32, you'll be able to only use 32. If you have 64, you will only be able to create models with size 64. And if you have 128, that is the same. So you'll only be able to create models with image size 128. But still remember, the higher you go, the more time it will take. So I will stick with 32 for now. I'm going to play this. And then it's the same way, the same code that we had last time. We're basically trying to create a model. So I'm going to play this one as well. And then we have what I would call the structure, the architecture of the model. So this is our current architecture. What happens is once you've created your model, this is also something that gets stuck with you in a way. When you're reloading your weights, you're essentially reusing the same architecture. You cannot really change much of it. It's just this top part has to stay the same later on. So I'm going to reuse the same architecture as last time. This is our custom CNN. And then I'm gonna look at the summary. So it's the same, it rescales, three convolution layers, three max pooling layers, it flattens, and then we have two dense layers. So this is the output. It gives us our total params. This is a very shallow model, so not that very huge. And then we compile, and then essentially we will be training this. Um, I don't think this will take too much time, so I'm just gonna play it. So while this plays, it will create a new model. So at the end, you would be testing your model to see if it worked well. When I was doing this, I'd get 92% accuracy, and these were my curves. And then I ran a confusion matrix, and I got this. It's not a very good model. It is a little bit overfitting on some things and underfitting on some things, but this is just a demo just to show you what transfer learning is. So essentially, once you're finished training, once you have evaluated your network, once you're happy with your accuracy and your metrics, what you want to do is you want to save the weights. The biggest part is these weights. And we don't just use model.save, we use model.save weights. And I have a new file. There is a naming scheme for this. It has to have the .weights.h5 to be able to save correctly. If you don't save it correctly, it will give you issues later on. So this is how we save weights. I do have this in the folder weights, custom cnn.weights.h5. If you're following through, you can just import it. You don't have to rerun everything. So this is us weight training, and you might have to go through this a couple of times to get it right. So now in transfer learning, this is transfer learning with a shallow model. So it's not perfect. It follows the same steps. So you'd be um, installing your packages. If they're already installed, you don't have to do it again. And then now, rather than importing our vegetable data set, we're importing our fruit data set because now we're trying to transfer what we learned from vegetables into fruits. Similarly, we have the image size of 32. We're now locked into 32 because our weights were built with 32. So because this was built with 32, that means we have to continue with 32. If we try to override it and write 64, we'll get errors. This will not work. So once your model is trained a certain way, you have to use that image size, that input size. So I'm gonna play this, and then we'd have the same code, nothing really changes. You're loading your data. We have the same layers, right? Similarly, we're having 15 outputs because the weights were trained with 15 outputs. So once this is played, we want to see the summary for this. And this will show you the exact same thing. I think it's still importing. Let it run. It will show the summary soon. So what we're trying to show is that we have the same structure as before. This is exactly the same as we had in weight training. Nothing has changed so far. What's not changing is this part. The first thing is you need to load the weights from your vegetable data set. And then what you're trying to do is you're trying to remove the last layer. And what we're trying to do is just get rid of this last one. So indexing is something arrays do. For example, if you have an array, let me create a new code block. If you have, let's say, values, and you have the values 10, 20, 30, 40, 50, and 60. I'm just going to show you what this does. So if I say I want values, and I just want, for example, I want value 0, this will give me the value 10 because this represents the zeroth thing in this list. So 0 index means the first, and then the first index means the second. So a numbering with index starts at 0 and then it goes on onwards. So if I say that I have values 1, it will take the second object. So this will give me 20. And similarly, if I want to go all the way to the end, this would be 0, 1, 2, 3, 4, 5. So I'd have 60. Similarly, going backwards, the first value is not -0 because that does not exist. So the value will be -1. That will give me 60. If I go backwards, -2, that will give me 50, and so on and so forth. So this is -1, -1, -2, -3, -4, -5, -6. So if I put -6, that will give me 10. So now if I want to, I'd say slice, let me just write this down. Slice or slicing is the process of cutting an array or a list, and it's represented by having a number and then another number with a colon in the middle. And what this means is cut the number from the first index to the second index. So if I do this, I will only get this number. This is the number between these two. So if I want to have 10 and 20 in this list, I would have to include this much. So this is the start and this is the stop. This will give me this list. And what this means is that I want you to just start anywhere. However, I want you to remove the end. So if I say this, what I'm trying to say is just get me everything except the last one. So what we're trying to do with our model is that we're trying to take everything except this 15. And this is because we're trying to remove it so that we can keep um, the three values, because with fruit data set, we only have three. We don't have 15 as the way this one has. This has 15 value, this one only has three. So we're trying to remove this last layer so we can keep three. So we have removed the last layer, and then we're going to rebuild this model. And when you look at it now, you'll see that that 15 is gone. It stops at 128. Now we want to add our three layer. So we're going to um, let this not be trainable, put trainable to false. So it means everything inside of those layers are false. And then we're going to just select from the last two layers, we're going to say only I want to only train the last two layers. And then I'm going to keep my model, which is this model. And then I'm going to add three values to my dense layers, three new nodes to it, because this is going to be my apple, my orange, and my banana. Now, once you're here, technically, you can add as many layers as you want. You can recreate um, your whole architecture if you want. You can add more stuff. For example, I could say I want to have ReLU here. That is up to you. However, for this, I just want to have it simple. I just want to change that 15 to 3. So what I'm going to do is I'm just going to play this, and we're going to continue. The thing you should know is transfer learning is something we do with deep networks, ones with lots of layers. We only have technically three valid layers. So doing transfer learning on this is as good as useless, but we're just doing this so you can understand the concept. And doing this with a small network first helps you run this a lot of times so you can understand the concept. So just go through this knowing that you may not get really, really high accuracies for now. We're just learning. When you look at the summary now, you'll see that we have the original one, which ended at 128, and then we have a new dense layer that adds the three new nodes. So once you're done the same process, we're going to compile the model and then fit it. So you're training it for 20 epochs with the same data, which is the fruit data, the apple, the banana, and orange. So it will train, um, you'll get maybe some accuracies between 30 all the way to 80. Oh, this one's getting to 90. That's okay. That's good. So once you finish training, now it's the same process as before. What you're trying to do is you're saving the model. You're just continuing, like you're getting a perfectly fit model. Then you have to ensure that you have good accuracy, you have good loss, and then similarly, you're trying to ensure that you have a good confusion matrix. So I'm going to wait for this to finish. It's not taking that much time. So it's at 13 epochs with 92% training accuracy and 84 on this side. Validation, it is sort of jumping up and down, so it's not very, very good. Also, the loss is going up and down. So the model is most likely overfitting onto the data, but we're just sort of showing you what's happening. So let's just continue this. Okay, it's almost done. It gave us a validation accuracy of 79%. So I'm just gonna save this, and then I'm going to look at the graphs. Yeah, it is overfitting onto the training data, but that's okay for now. This is just to show you the progress. What you'd need to do most likely is change the learning rate, make it a little bit smaller. I think the data is augmented. Maybe you could augment a little bit heavier. But for now, let's just continue with the script. So when we continue with this, we get a precision of 82% and a recall of 77 with an F1 score of 76. And you can see it tries to get everything right, but you do see some underfitting and overfitting with some of the stuff. With bananas, it has predicted 8 wrong. With apple, this is 5 wrong. With orange, it's okay, it's at 9. And I'm going to try using this specific model to predict the orange image. Let's see how good it is. Okay, it's okay. It says orange with 81% accuracy. So what we're trying to do is we're trying to use transfer learning. The weights were from the custom weights with our shallow model, and it seemed to be fine. So now this is when you have a shallow model. What if you wanted something bigger? What if something you do not know about yet? And that's what pre-trained models are for. So most people do confuse what pre-trained model are. Pre-trained models are models that have already been trained. These can be models that are not, let's say, big in names, that are not known, as long as they're trained. Like for example, these weights. This came from a pre-trained model. Um, what you're trying to do is you're trying to find these big architectures that are known, that have been verified, and that are pre-trained. So when you go to applications, all of these models on your left side, these are very famous models. These are models that are known, that have been tested on different data, most likely ImageNet, and they work really, really well. They're verified. That's the concept. And they offer pre-trained versions of them. And with TensorFlow, most of these models have, I'd say, boundaries, like choke points where you can't really edit them. And the biggest choke point is the input shape. Most input shapes, you'll see them stuck at 224 by 224 image size. If you go, let's say, to another website, let's say Microsoft, for example, they might offer a MobileNet V2 that has been pre-trained with a different set of numbers. So for example, if you want VGG16, um, let's see if it loads. Okay, for VGG16, it loads the same way. The default input size for this model is 224 by 224. It just works really, really well with this input size. However, the different websites can give you different input sizes if you need them. Most likely, you might be stuck with this for a while. So I guess get comfortable with this. This is a really big image size to train with. It might consume a lot of power on your computer. If you're finding it really, really difficult to train with this, I'd suggest you do maybe online training, or that you have a really, really powerful computer that you can train with. So today we're going to stick with MobileNet V2 because it is lightweight. It has, I think, 155 layers, and it has 155 layers, and the simple shape is 224 by 224. Even though there are a lot of layers, it does take less time to train because the layers are very, very light. They don't have a lot of, I'd say, heavy convolutional filters. So we're going to use MobileNet V2. The code is given to you on how to import all of these networks into your code. So I'm going to start at the top. Same concept. We install our packages if you don't have them. And then now we would be importing our data set. Um, so first thing is we have to remember is we have to change the image size because now we're using 224. I'm going to wait for this to finish loading. I think it wants to stop loading. Let me refresh the kernel. Okay, let's see if it will import again. Okay, now it's sticking. So we have to stick with this image size because our model that the pre-trained version of this model is at 224. So I'm going to show you two versions of all of this. The first step is to use a verified model and not take in all the weights. And the second step is to take in all the weights. So I'm going to import all of my images. We have the same images, so apple, banana, and oranges. And then now, this was the original code. This was where we were, but this time I don't want to use this. So I'm just going to comment this. To comment, for Windows, it's control forward slash. On Mac, it is command forward slash. So if you select and do that, it will comment and uncomment. I think there is also some selection, maybe somewhere in here to comment. I'm not so sure where it is, but it's in here somewhere. I think it's toggle block comment. No, it's not the one. One of these two will comment and uncomment your code, but the shortcut, write this down here. Control plus forward slash or command plus forward slash to comment and uncomment your code. So we have this code that we're trying to import. I'm just going to copy this and I'm going to paste it there. So this code, I want to save it somehow. So I'm going to call it my model. My model is now MobileNet V2. It does not take any input. It has an alpha, there's something called include top, and then we have weights, an input tensor, some pooling, and some classes. So if you want MobileNet V2 fresh, if you don't want any weights at all, the first step is to declare that you first have to declare how many classes you want. Let's go from all the way from the bottom all the way up. So we want how many classes do we want? We have three. So there were three classes. The pooling is just the average pooling, which will reduce the size of your images. I don't really have an input tensor at the moment. If it's fresh, we don't need any weights. So I'm just going to keep this to none. And do I want to include the top from MobileNet V2 with 1,000? No, I'm going to set this to false. And then the input shape. So the input shape describes the size of your MobileNet. So for example, if you wanted a fresh version of this, you'd have to keep the image size, height, and width. So for example, let's say just because we're making it fresh, let's say I had 64 here. That means I could keep 64 as my height, 64 as my width, and then I'd have the three channels of RGB. If I was to play this, you see that we have a model. Let me get a history of this, a summary of the model, model.summary. You'll see that we have a MobileNet V2 with 64 by 64. So that means this is a fresh model. It is very long. If you scroll, it feels like eternity, but you'll get all the way to the end. And wait, sorry, I think we need to keep this as true. I do want the output. Okay, and then I'm going to replay the summary so you can see this. Okay, so the predictions is 3 because we have 3 classes at the end. And it's a very small model, so it's 8.6 megabytes. Then I would continue training as the way I did it before. So this is a fresh version of MobileNet. So if I was to play this, it would learn everything from scratch. It says I have an error. It says expected 64, 64, found 224, 224. So I think there's another place I may have accidentally kept 224. Let's go see. Where did I keep 224? I think the images were cut to this size. So let me just replay everything. It should be fine. So I'm just going to replay this. Replay this. I'm going to replay that. Summary should be the same. And then I'm going to compile and run this. So this should train a very fresh MobileNet V2 model for you. I'm just going to let it run maybe for 1 or 2 epochs, and then I'm going to show you the transfer learning method. So this will train a fresh version. There's nothing wrong with training it fresh. You might want to try it first with your images to see if you get really good accuracy. But with transfer learning is that you have a chance to boost your accuracy later on. So if this was to train all the way to the end, it will train a certain value. I'm going to let it run while I make changes at the top. So, for example, let's say you don't have enough images. Let's say you only have 100 images in your data set, and you can't maybe augment it too much, and you want to use MobileNet V2. But if you want to use transfer learning, you have to stick with the rules. So the rules for this specific model that you have imported is that image size has to be 224. So I'm going to play with 224 when it reruns a second time. Um, Then I want my input shape to be that same way that it was trained last time. So one way I could do this, I could say 224 by 224. That's one option. Or I could just take the same values that were given before me because this was the original version. So I can just say none. What none means is the same as saying 224 by 224 by 3. It just means I'm not making any changes to this model. I want the default version. So this stays the same. And now we have include top and we have weights. So the same way we did transfer learning, when we had this model, we had to import the exact version of that model so that we could load those weights. We could not say, I wanted 3 values here. So that means you have to take all of the 1000 classes inside the mobile VNet as you load the weights. So I'm going to have the same values the whole way. And then I have an option here. Do I want to include the top? This is the same as this line over here where I'm trying to cut something, where I'm saying I want to remove the last layer. So when I say I want this to be false, it just means I'm going to remove that last 1000 dense nodes so that I can keep my own. So now I'm importing a MobileNet v2 with ImageNet. If you run this for the first time, it might try to download it and it might take a minute. Especially with the bigger ones, it might take a lot of time. So this will run and this will tick. Let's just go to the bottom to see how far the training has done. It's at 19 and it's progressing really, really well. So I don't really want to finish this version of the code. I'm just going to stop it. I want to show you transfer learning. So let's go to the top. I'm going to play this. I'm going to get my images and I'm going to get my ImageNet weights with MobileNet V2. So this will tick. If I look at the model summary now, it should change. Sorry, I think something we have not saved it here. So I'm going to play this and then I am going to get this. You'll see that we have none, 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 which is the default values. And it's really, really long. And then all the way to the end, which has 1280. So this does not have a bottom of its own. So you have to add it manually. So because there is no end to it, there's no way you can predict with this, means you have to add something to it. It's it's a model with a start, but without an end. So let's go here. And what we can say is I have a model. What I want to do is I want to add a dense layer. So I could say I'm going to uncomment this, and then I don't really need any of this anymore. I just want my model. I just want this. So what I can do is I can just keep model there. So take the model, it will flatten all the 1280 nodes, and then it will add one more layer. This is not important, just kept it because it was there. And then we have the final one, which is 3. Here you can add as many layers as you like if you want. You can improve your accuracy that way. If I play this now, I think there's a little error. It says shapes used to initialize none. 928. I think it is very specific now. We have to actually type these values. Okay, let's play it again. Okay, it's fine. Okay, so it's fine this time. We have the mobile net values. They end with 1280. And then you flatten them, you get another dense layer, and then finally you have three values. And then we can compile the model and then train it. So this time we're using all of the weights from ImageNet, which is all the like random images, common objective images that are available in ImageNet. And we're trying to use those weights to be able to predict my fruit dataset. And sometimes this can really improve your accuracy dramatically. So let's say you're stuck on 30% accuracy. Using transfer learning can boost it up from like 30 all the way to 80%. Let's say you're stuck at 80%, this can boost you all the way to 90, 95%. So transfer learning is really, really useful, and especially if you don't have enough data or if you want to use a really heavy and dense network, it would be wise to start off with a pre-trained version of it so that it's in a sense warmed up for you. So this will take time. Whenever you sit and look at a model train like this is a process called babysitting. What you're trying to do is you're trying to watch it. Right now, it's very friendly because it does not take that much time. You can see it only goes through 96 iterations in this epoch. However, this one epoch could go from being 71 seconds all the way to maybe 3 hours. So sometimes you just have to sit and watch your model as it trains correctly, as it jumps from a certain accuracy to another one. So similarly, this will keep going, and you will reach a step of maybe saving the model. You reach a step of evaluating the model, has it trained correctly. You'll reach a step of looking at the matrix, seeing if it worked correctly, and testing it with images, seeing if everything is okay. So this will work for you. However, sometimes, let's say you don't want to use the ImageNet version of these models. Let's say you want to train on data that's on your own. So for example, here we do have vegetable data set. Maybe ImageNet worked for me. Maybe I got to 95%, and maybe I want to increase it by using data that is closely related to my data. So for example, if you have, so for example, I have fruits, I'm trying to use vegetables to supplement those fruit. If you have maybe some kind of medical images, you try to use another set that you can find a lot of data on it, and then later on transfer learn using your own data set. So I have another script that's called wait for vegetables. What it does is the same as this weight training over here, but this time I am using an empty version of the mobile net. So I'm just using an empty version of everything and I'm trying to create it. This one is 64 by 64. It'll create my network and then it will train it. It will run it for 20 epochs. I ran it for 20 epochs. I got 95% accuracy. And then I did some graphing. This was my graph. It's okay. It's not perfect. It's okay. Um, Essentially, this is something I should say that you should test and evaluate your model before saving. I skipped this just so you could do this very, really quickly inside of the class. Um, so the same thing as last time, you want to save the weights. So you can save the complete model and then extract the weights later, but essentially what you want to do is you want to save the weights themselves. So to save them, I will rewrite this. You write the model, the name that you saved it, the value, which is this one, the model. And then you want to use a function called save underscore weights. And then you give it the path, which is currently dot weights. And I named it mobile net vegetables dot weights dot h5. So your weights have to end with dot weights dot h5. And you can rerun this on your own, maybe try and improve that accuracy from 95, maybe all the way to 99. And then you'll get a new weight version. And this whole concept is that rather than using ImageNet, you try to use your own weights. So I'm going to stop this. It's currently at 96% accuracy. And what you'd want to do is you want to change some stuff. So remember, whatever changes you made on this side have to be similar on this side. I use an image size of 64. That means I have to change my image size here to be 64. If you retrain this and you write 224 here, then your new weights will be for 224, so you can continue 224. So mine is currently 64. I'm going to change my input shape to be 64 by 64. And similarly, I don't want to include the top. And I have a new weight, and my weights are in weights, mobile net vegetable dot weights. So I'm keeping an actual value for my weights. Um, Now you have to be careful because the classes are not 1000 anymore. The classes are 15 because we kept it as 15 here. So this will change from 1000 to 15. Everything else looks fine for me. And I just want to keep the same values here. And then this is fine. So what I want to do is I want to run all of this. So I'm going to run this. I'm going to import my images. I'm going to define my layers. Okay, I'm going to look at the summary. It's the same thing. It gets to 3. It is it's not that big, 11.12 MB. And I want to train it. You can always change the learning rate as you wish, just so you can see it trained differently. So I've compiled it, and now I want to fit it with 30 epochs. So this time I'm training using my vegetable weights. So the vegetable weights were just trained, they're not perfect, but it's just a way to show you that you can make your own weights on the model and then do it yourself. So this is training is currently starting at 55%. If you started off without the weights, it might start off at 10%, for example. So it might not start off really, really well, but because it had a jump start, I guess it will train very, very well. So I'm going to let this run, and I guess you might see the final value on GitHub or inside the class when you see it. So similarly, now I'm actually training a model. So at the end, you'll want to save it. I'm going to call this MobileNet V2 model. And once that's done, it will save this as well. It will appear somewhere inside of models. I'm going to plot this, and then I'm going to check for the confusion matrix, the precision, the recall, and the F1 score, and then I'm going to test it at the end. So these values will appear for you if you touch the script later on. I am ending this video early so that we have a shorter video this time for you guys to watch. However, I would like for you to try different things, try the weight values, these ones, try and make the image as a little bit bigger, see what that does, see how you can change it inside of the pre-trained models on your own. Try not to get the errors. Everything should work correctly and okay. Once you're done inside of pre-trained models, once you're comfortable with a MobileNet V2, try and use a different architecture. Try EfficientNet B0. This one is also lightweight. It's not that heavy. It will take less time to download. When you're comfortable, try a bigger model like VGG16. VGG16 just means that this is a model that has 16 layers. If you need to know more about it, you can go and view the source on GitHub. You can read about it in some of the articles that have they published in, or you can go to Google and search what VGG16 is. So I could just type what is VGG16, and it will show me, it will give me a description of what it is. This is a CNN architecture with 16 layers of a network, and it will tell me where it was developed, what it does. VG16 is really, really good. Most of the times, if you try this, it will most likely work for a lot of the image classifications that you have. There is an article about it on Medium. This article is really, really good at describing what it is and what it does and how you can get working with it, and its architecture and how it was built. The architecture itself, it tells you it has 21 layers, but only 16 valid layers because there's only 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 valid layers that are trainable. That's why they call it VG16. So similarly, when you're talking about VG19, there's only 19 valid layers. So try these. They're not very, very heavy. When you're feeling very, very courageous, try the bigger models like Resident 50. This might take more time for you to train, especially if you're working on a computer that is doesn't have enough resources like RAM. I would not recommend training anything above 50 layers on your laptop. It will probably not work, or it will take way too much time. Images like ResNet 101 going upwards, try and stay away from them on your own laptop because they will consume a lot of your memory. You will find that your whole computer becomes unresponsive. So if you're not training online on servers, stick away from these really, really large networks. So that is it for this week. If you have any questions, I'm available. If you're stuck anywhere, let me know. Currently, our model is raining. It has reached 98% accuracy with our vegetable weights. So I'm just going to let this finish so that we can see the rest of the code. Okay, this is the final epoch. Validation is not really, really good. It's at 80%, but it is close enough to 90. Let's see how well it did. So the graph looked like this, 100% overfitting, but you can improve this by slowing down the learning rate, maybe also tweaking this part as well. Okay, let's look at the confusion matrix. It's okay, but still some stuff are wrong. With orange, it is misclassifying 1. With banana, it's misclassifying 5. And with apple, it's misclassifying 3. The precision is 85%, which is okay, but not really good. It has to go all the way to 90 to be a really good model. And then I think I changed the name of the model. It's called MobileNet V2. I'm going to copy that and I'm going to import it here. Okay, I'm just going to play. And then it says that the orange was orange by 79%. Let's try a different image to see how well it does. The banana is 100% accurate, apparently. It says it's, and then I think we have orange 30. Let's see if this gets correct. It also thinks it's orange. So it's okay, it's not perfect, but this is how you use transfer learning.